Hi, I am a tutor in Uplatz. Today we are going to discuss about C traps and pitfalls part 1. The C language is a carving knife, simple, sharp, and extremely useful in skilled hands. Like any sharp tool, C can injure people who don't know how to handle it. This paper shows some of the ways C can injure and vary and how to avoid injury. Introduction. The C language and its typical implementations are designed to be used easily by experts. The language is terse and expressive. There are few restrictions to keep the user from blundering. A user who has blundered is often rewarded by an effect that is not obviously related to the cause. In this paper, we will look at some of these unexpected rewards. Because they are unexpected, it may well be impossible to classify them completely. Nevertheless, we have made a rough effort to do so by looking at what has to happen in order to run a C program. We assume the reader has at least a passing acquaintance with the C language. Section 1 looks at the problems that occur while the program is being broken into tokens. Section 2 follows the program as the compiler groups its tokens into declaration, expression, and statements. Section 3 recognizes that the C program is often made out of several parts that are compiled separately and bound together. Section 4 deals with misconceptions of meanings, the things that happen while the program is actually running. Section 5 examines the relationship between our programs and the library routines they use. In the section 6, we note that the program we write is really the program we run. The preprocessor has got first. Finally, section 7 discusses probability problems, reasoning. A program may run on implementation and not another. Lexical pitfalls. The first part of a compiler is usually called a lexical analyzer. This looks at the sequence of characters that make up the program and breaks them into tokens. A token is a sequence of one or more characters that have a relatively uniform meaning in the language being compiled. In C, for instance, the token has a meaning that is quite distinct from that of either of the characters that make it up, and that is independent of the context in which the equal to appears. For example, consider the statement: if x greater than big equal to x. Each non-blank character in this statement is a separate token, except for the keyword if and the two instances of the identifier big. In fact, C programs are broken into tokens twice. First, a preprocessor reads the program. It must tokenize the program so that it can find the identifiers, some of which may represent macros. It must then replace each macro invocation by the result of evaluating that macro. Finally, the result of the macro replacement is reassembled into a character stream, which is given to the compiler proper. The compiler then breaks the stream into tokens as a second time. In this section, we will explore some common misunderstandings about the meaning of tokens and the relationship between tokens and the characters that make them up. We will look about the preprocessor later. Equal to is not equal to. Programming languages derived from algorithms such as Pascal and Ada use colon equal to for assignment and equal to for comparison. C, on the other hand, uses equal to for assignment and equal to for comparison. This is because assignment is more frequent than comparison, so the more common meaning is given to them. Moreover, C treats assignment as an operator so that multiple assignments such as A equal to B equal to C can be written easily, and assignments can be embedded in larger expressions. This convenience causes a potential problem. One can inadvertently write an assignment where one intended a comparison. Thus, this statement looks like it is checking whether X is equal to Y. If X is equal to Y, who actually sets X to the value Y, and then checks whether the value is non-zero, or considers the following loop that is intended to skip blanks, tabs, and new lines in a file. While C equal to blank, or C equal to slash tab T, or C is equal to N slash N, C get C, F. The programmer mistakenly used equal to instead of equal to in the comparison with backslash T. This comparison actually assigns a \t to C and compares the new value of C to 0. Since \t is not 0, the comparison will always be true, so the loop will hit the entire file. What it does after that depends on whether the particular implementation allows a program to keep reading after it has reached the end of file. If it does, the loop will run forever. Now, some C compilers try to help the user by giving a warning message for conditions of the form E equal to E2, E1 equal to avoid warning messages from such compilers. When you want to assign a value to a value variable and then check whether the variable is 0, consider making the comparison explicit. In other words, instead of if x equal to y, foo, right? If x equal to y not equal to 0, foo, this will also help your intentions blind. And or not and or. It is easy to miss an inadvertent substitution equal to because so many other languages use equal for comparison. It is also easy to interchange and or, especially because the and or operators in C are different from their counterparts in some other languages. We will look at these operators more closely in section 4. Multi-character tokens. Some C tokens such as slash, star, and equal to are only character long. Other C tokens such as slash, star, and equal to and identifiers are several characters long. When the C compiler encounters a slash followed by an star, it must be able to decide whether to treat these two characters as two separate tokens or as one single token. The C reference manual tells how to decide if the input stream has been parsed into tokens up to a given character. The next token is taken to include the longest string of characters, which could possibly constitute a token. Thus, if a slash is the first character of a token and the slash is immediately followed by a star, the two characters begin a command regardless of any other context. The following statement looks like it sets y to the value of x divided by the value of pointed by p, y equal to x slash star p slash star p points at the divisor star slash. In fact, slash star begin command. So the compiler simply gobble up the program text until the star share slash appear. In other words, the statement just sets y to the value x and does not even look up at p. Retaking the statement as y equal to x slash star p slash star p points at the divisor star slash, or even y is equal to x divided by within bracket star p slash star p points to at the divisor star slash would cause it to do the division, and the command suggests. This sort of nearby ambiguity can cause trouble in other contexts. For example, older versions of C use equal to plus to mean what present version are mean by plus equal to. Such a compiler will treat a is equal to -1 as a meaning the same as thing a is equal to -1 or a is equal to a -1. This will surprise a programmer who intended a is equal to -1. On the other hand, compilers for these older versions of C would interrupt a equal to slash star b as a equal to slash star b, even though the slash star looks like a command. Exceptions, compound assignment operators such as plus equal to are really multiple tokens. Thus, a plus slash star strange slash star equal to 1 means the same as a plus equal to 1. These operators are the only cases in which things that look like single tokens are really multiple tokens. In particular, P assigned to A is illegal. It is not a synonym for P assigned to A. As another example, the operator greater than operator is a single token. So greater than equal to is made up of 2 tokens and not 3. On the other hand, those older compilers that still accept equal to plus as a synonym for plus equal to, treat equal to plus as a single token. Strings and characters, single and double quotes mean very different things in C. There are some contexts in which confusing them will result in surprises rather than error messages. A character enclosed in single quotes is just another way of writing an integer. The integer is the one that corresponds to the given character in the implementation's collating sequence. Thus, in an ASCII implementation, A means exactly the same thing as 0141 or 97. A string enclosed in double quotes, on the other hand, is a shorthand way of writing a pointer to a nameless array that has been initialized with the character between the quotes and an extra character whose binary value is 0. The following two program fragments are equivalent: printf hello world \n within double quotes, character hello HELLO VORLD \n0 print hello. Using a pointer instead of an integer or vice versa will often cause a warning message. So using double quotes instead of single quotes or vice versa is usually caught. The major exception is in function calls, where most compilers do not check argument type, thus saying print within quotes \n instead of print within double quotes \n will usually result in a surprise at runtime. Because an integer is usually large enough to hold several characters, some C compilers permit multiple characters in a character constant. This means that writing yes instead of yes within double quotes may well go undetected. The latter means the address of the first of the 4 consecutive memory location containing Y, E, yes, and a null character respectively. Within quotes, the format means an integer that is composed of the values of the character Y, E, S in some implementation defined manner. Any similarity between these two quantities is purely coincidental. Syntactic pitfalls. To understand a C program, it is not enough to understand the tokens that make it up. One must also understand how the tokens combine to form declarations, expressions, statements, and programs. While these combinations are usually well defined, the definitions are sometimes counterintuitive or confusing. In this section, we look at some syntactic constructions that are less than obvious. Understanding declaration. I once talked to someone who was writing a C program that was going to run standalone in a small microprocessor. When this machine was switched on, the order would call the subroutine whose address was stored in location 0. In order to simulate turning on power on, we had to devise a C statement that would call the subroutine explicitly. After some thought, we came up with the following: star while star bracket open bracket close 0 bracket close bracket open bracket close semicolon. Expression like this strike error into the hearts of the C programmers. They need not tough because they can usually be constructed quite easily with the help of a simple rule. Declare it the way you use it. Every C variable declaration has 2 parts: a type and a list of stylized expressions that are expected to evaluate to the type. The simplest such expression is a variable -3 minus variable float f comma g indicates that the expression f and g when evaluated will be of the type float because the thing declared is an expression. Parentheses may be used freely. Float parenthesis f parenthesis means that f within double parentheses evaluates to a float, and therefore by inference that f is also a float. Similar logic applies to functions and pointer types. For example, float ff parenthesis open close means the expression ff parenthesis is a float, and therefore ff is a function that returns a float. Analogously, float star pf means that star pf is a float, and therefore that pf is a pointer to a float. These forms combine in declaration the same way they do in expressions that float star g bracket open close comma within bracket star h bracket close bracket open close semicolon say that star g and star h are float expressions since bracket binds more tightly than the star. Star g means the same thing as star within bracket G, bracket open, bracket close, colon G is a function that returns a pointer to a float, and H is a pointer to a function that returns a float. Once we know how to declare a variable of a given type, it is easy to write a cast for that type. Just remove the variable name and the semicolon from the declaration and enclose all things in parentheses. Thus, since float star G, parenthesis open, close, semicolon declares a G to be a function returning a pointer to a float, bracket open, float star, bracket open, bracket close is a cast to that type. Armed with this knowledge, we are now prepared to tackle bracket open, star, bracket wide, within brackets, star, bracket open, bracket close, 0, bracket close, bracket open, close. We can analyze this statement in two parts. First, suppose that we have a variable fp that contains a function pointer, and we want to call the function to which fp points. This is done this way: bracket open, star, fp, bracket close, bracket open, close, semicolon. If fp is a pointer to a function, star fp is the function itself. So within brackets, star fp, bracket close, bracket open, bracket close is the way to re-invoke it. The parentheses in bracket open, star fp, bracket close are essential, because that the expression would otherwise be interpreted as star, bracket open, fp, bracket close, bracket open, bracket close. We have now reduced the problem to that of finding an appropriate expression to replace fp. This problem is the second part of our analysis. If C could read our mind about types, we could write bracket open, star 0, bracket close, bracket open, bracket close. This does not work because star operator insists on having a pointer as its operand. Furthermore, the operand must be a pointer to a function so that the result of star can be called. Thus, we need to cast 0 into a type loosely described as pointer to function returning void. If fp is a pointer to a function returning void, then bracket open, star fp, bracket close, bracket open, bracket close is a void value, and its declaration would look like this: void, bracket open, star fp, bracket close, bracket open, bracket close, semicolon. Thus, we could write void, bracket open, star fp, bracket close, bracket open, bracket close, bracket open, star fp, bracket close, bracket open, bracket close, cost of declaring a dummy variable. But once we know how to declare the variable, we know how to cast a constant to that type. Just drop the name from the variable declaration. Thus, we cast 0 to the pointer to function returning void by saying void, bracket open, void within bracket stars, blank star, bracket close 0, and we can now replace fp by void, bracket open, void, within bracket star, bracket open, bracket close, 0, colon, bracket open, star, void, bracket open, void, bracket open, star, close, bracket open, bracket close, 0, bracket close, bracket open, bracket close, semicolon. The semicolon on the end turns the expression into a statement. At the time we tackled this problem, there was no such thing as a type definition declaration. Using it, we could have solved the problem more clearly. Type definition void within brackets, star function pointer, bracket close, bracket open, bracket close, semicolon, or bracket open, star function pointer within bracket, 0, bracket close, bracket open, bracket close, semicolon. Operators don't always have the precedence you want. Suppose that the manifest constant flag is an integer with exactly 1 bit turned on in its binary representation. In other words, a power of 2, and you want to test whether the integer variable flag has that bit turned on. The usual way to write this is if flag and capital flag. The meaning of this is applied to most C programmers, and an if statement tests whether the expression is in the parentheses equals to 0 or not. And it might be nice to make this test more explicit for documentation purposes. If flag and flag not equal to 0, the statement is now easier to understand. It is also wrong because not equal to binds more tightly than and. So the interpretation is now if flag and capital flag not equal to 0, equal to 0. This will work by coincidence if flag is 1 or 0, and that is not, but not for any other power up to star. Suppose you have two integer variables h and l whose values are between 0 and 15 inclusive, and you want to set R to an 8-bit value whose lower order bits are those of the L and whose higher order bits are those of the H. The natural way to do this is to write R is equal to H less than 4 plus L. Unfortunately, this is wrong. Addition binds more tightly than shifting. So this example is equivalent to R equal to H less than 4 plus L. Here are two ways to get it right. Or within bracket H less than 4 plus L or H less than 4 or L. One way to avoid this problem is to parenthesize everything, but the expression with too many parentheses are hard to understand. So it is probably useful to try to remember the precedence levels in C. Unfortunately, there are 15 of them, so this is not always easy to do. It can be made easier, though, by classifying them into groups. The operators that bind the most tightly are the ones that are not really operators, subscripting functions, calls, and structure selections. These all associate to the left. Next come the unary operator. These have the highest precedence of any of the true operators because function calls bind more tightly than unary operators. We must bind within brackets star p bracket close bracket open close to a call function pointed to by p. Star p bracket open bracket implies that p is a function that returns a pointer. Casts are unary operators and have the same precedence as any other unary operator. Unary operators are right associative, so star p plus plus is interpreted as star of p plus plus and not as within bracket star of p plus plus. Next come the true binary operators. The arithmetic operators have the highest precedence, then the shift operator, the relation operator, the logical operator, the assignment operator, and the final, the conditional operator. The most important thing to keep in mind are every logical operator has low precedence than every relational operator. The shift operators bind more tightly than the relational operators, but less tightly than the arithmetic operators. Within the various operator classes, there are few subclasses: multiplication, division, and remainder have the same precedence. Addition and subtraction have the same precedence, and the two shift operators have the same precedence. One small surprise is that the 6 relational operators do not all have the same precedence. Colon equal to and not equal to bind less tightly than the other relational operators. This allows us, for instance, to see if A and B are in the same relative order as C and B by the expression A less than B equal to C less than D. Within the logical operator, no two have the same precedence. The bitwise operator all bind more tightly than the sequential operators. Each and the operator binds more tightly than the corresponding OR operator, and the bitwise exclusive OR operator XR was bitwise and bitwise OR. The ternary conditional operator has lower precedence than any we mentioned so far. This permits the selection of expression to contain logical combination of relational operators as in is equal to A less than B and B less than C question mark D colon E. This example also shows that it makes sense for assignment to have a lower precedence than the conditional operator. Moreover, all the compound assignment operators have the same precedence and they all group right to left so that A equal to B equal to C means the same as A, B equal to C, semicolon, A is equal to B, semicolon. Lowest of all is the common operator. This is very easy to remember because the comma operator, this is very easy to remember because comma is often used as a substitute for semicolon when an expression is instead of a statement. Assignment is another operator often involved in precedence mix-up. Consider, for example, the following loop intended to copy one file to another, while within brackets C is equal to get C of in, within bracket not equal to file, put C into out, semicolon. The way the expression in the while statement is written makes it look like C should be assigned the value of get C in, and then compared with E of F, end of file to terminate the loop. Unhappily, assignment has lower precedence than any comparison operator, so the value of C will be the result of the comparing get C in, the value of which is then discarded and EOF. Thus, the copy of the file will consists of a stream of byte whose value is 1. It is not too hard to see that example above should be written, while within double bracket open, C is equal to get C of in, within bracket close, not equal to E of F, put C, comma out, semicolon. However, error of this sort can be hard to spot in more complicated expressions. For example, several versions of the lint program distributed within the Unix system have the following erroneous line. If bracket open T is equal to B type, bracket open pointed to ATY equal to ST or TY, or T equal to uni OTY braces. This was intended to assign a value of to T, and then see if T is equal to ST or TY or union of TY. The actual effect is quite different. Dot star. The precedent of the C logical operator comes about for historical reasons. B, the predecessor of C as logical operator that correspond roughly to C's and R operators, although they were defined to act on bits. The compiler would treat them as and RR if they were in a conditional context. When the two usages were split apart in C, it was deemed too dangerous to change the precedence much star. What's those semicolons? An extra semicolon in a C program usually makes little difference. Either it is a null statement which has no effect, or it elicits a diagnostic message for the compiler, which makes it easy to remove. One important exception is after an if or while clause, which must be followed by exactly one statement. Consider this example: if x of I greater than big semicolon big x of I semicolon, the semicolon on the first line will not upset the compiler, but this program fragment meaning something quite different from if x of I greater than big x of I semicolon. The first one is equivalent to if x of I greater than big braces open close, big is equal to x of I, which is of course equivalent to big is equal to x of I, unless x I or big is a macro with side effects. Another place that a semicolon can make a big difference is at the end of the declaration, just before a function definition. Consider the following fragment: struct foo braces open init x semicolon braces close f bracket open close braces open close. There is a semicolon missing between the first braces and the f that immediately follows it. The effect of this is to declare that the function f returns a struct foo, which is defined as a part of this declaration. If the semicolon occurs, f would be defined by default as a returning to an integer. Switch statement C is unusual in that the cases in a switch statement can flow into each other. Consider, for example, the following program fragment in C and Pascal: switch color, case 1 print up red, break, case 2 print up yellow, break, case 3 print up blue, break, braces close, case color color of 1 red, red, 2 red, yellow, 3 red, blue, end. Both these program fragments do the same thing, print red, yellow, or blue without starting a new line, depending on whether the variable color is 1, 2, or 3. The program fragments are exactly analogous, with one exception: the Pascal program does not have any part that corresponds to C break statement. The reason for that is that the case labels in C behave as two labels. Control can flow unimpeded right through a case label. Looking at it another way, suppose the C fragment look more like a Pascal fragment. Switch color within braces, case 1 print up red, case 2 print up yellow, case 3 print up blue, and suppose further that color were equal to 2, then the program would print yellow, blue, because control would pass naturally from the second printf call to the statement after 8. This is both a strength and weakness of C switch statement. It is a weakness because leaving out a break statement is easy to do and often gives rise to obscure programming behavior. It is a strength because by leaving out a break statement deliberately, one can readily express a control structure that is inconvenient to implement otherwise. Specifically, in large switch statements, one often finds that the processing for one of the cases reduces to some other case after a relatively small amount of special handling. For example, consider a program that is an interpreter for some kind of imaginary machine. Such a program may contain a switch statement to handle each of the various operation codes on such a machine. It is often true that a subtract operation is identical to an add operation after the sign of the second operand has been inverted. Thus, it is nice to be able to write something like this. Case subtract operand 2 is equal minus operand 2. No break, case add. As another example, consider the part of a compiler that skips white spaces while looking for a token. Here, one would want to treat spaces, tabs, and new lines identically, except that the new line should cause a line counter to be incremented. Case \n within quotes, line count plus plus, no break. Case \t, case quotes colon. Calling function, unlike some other programming languages, C requires a function call to have an argument list even if there are no arguments. Thus, f is a function. F bracket open close is a statement that calls a function that, but f semicolon does not nothing at all. More precisely, it evaluates the address of the function, but it does not call it. The dangling else program, we would remiss in leaving any discussion of syntactic pitfalls without mentioning this one. Although it is not unique to C, it has built-in C program with many years of experience. Consider the following program fragment. If x equal to 0, if y equal to 0, error, bracket open close semicolon, else within braces, z is expressed by f is equal to end of z, bracket close semicolon, brace, end of brace. The programmer's intention for this fragment is that there should be two main cases, x is equal to 0 and x1 equal to 0. In the first case, the fragment should do nothing at all unless y is equal to 0, in which case it should call error. In the second case, the program should set x is equal to x plus y and then call f with the address of z as its argument. However, the program fragment actually does something quite different. The reason is the rule that else is always associated with the closest unmatched. If we were to intend this fragment the way it is actually executed, it would look like this. If x equal to 0, bracket close, braces open. If y equal to 0, error of 0, else braces open, z is x plus y, f end of z, braces close. In other words, nothing at all will happen if x 0 to get the effect of implied by the indentation of the original example. Right, if x equal to 0, braces open. If x is 0, y is equal to 0, error. Else x is equal to x plus y and z, braces close. Linkage, a C program consists of several parts that are compiled separately and then bound together by a program usually called a linkage editor or a loader, because the compiler normally sees only one file at a time. It cannot detect errors whose recognition would require knowledge of several source program files at once. In this section, we will look at some errors of that type, some C implementations, but not all have a program can call lint that catches many of these errors. It is impossible to overemphasize the importance of using such a program if it is available. You must check the external type yourself. Suppose you have a program divided into two files. One file contains the declaration init n and the other contains the declaration long n. This is not a valid C program because The same external name is declared with two different types in the two fields. However, many implementations will not detect this error because the compiler does not know about the contents of either of the two fields while it is compiling the other. Thus, the job of checking type consistency can only be done by the linker or some utility program like lint. If the operating system has a linker that does not know about data types, there is a little the C compiler can do to force it. What actually happens when a program is run? There are many possibilities. The implementation is clever enough to detect a type clash. One would then expect to see a diagnostic message explaining the type of n was given differently in two different files. You are using an implementation in which init and long are really the same type. This is typically true of machines in which the 32-bit arithmetic comes most naturally. In this case, your program will probably work as if you had set long or init in both declaration. This will be a good example of a program that works only by coincidence. The two instances of n requires different amounts of storage, but they happen to share storage in such a way that the values are sent to one or valid for the other. This might happen, for example, if the linker arranges for the init to share storage with the lower part of the long. Whether or not this happens is obviously machine and system dependent. This is an even better example of a program that works only by coincidence. The two instances of n share storage in such a way that assigning a value to one has the effect of apparently assigning a different value to the other. The program is probably file. Another example of this sort of thing happens surprisingly often. One file of a program will contain a declaration like char file name, square bracket open close equal to etc password. Another will contain this declaration char star file name semicolon. Although the arrays and pointers behave very similarly in some contexts, they are not the same in the first declaration. The file name is the name of the array of characters. Although use the name will generate a pointer to the first element of that array. That pointer is generated as needed and not actually kept around. The second declaration, file name is the name of the pointer. That pointer points whether the programmer makes it point. If the programmer does not give it a value, it will have a zero null value by default. The two declarations of file name use storage in different ways. They cannot coexist. One way to avoid type clashes of this sort is to use a tool like lint if it is available in order to be able to check for the types of clashes between separately compiled parts of a program. Some programs must be able to see all the parts at once. Typical compilers does not do this, but List does. Another way to avoid this problem is to put external declaration into include fields. That way, the type of an external object only appear once. Semantic pitfalls. A sentence can be preferably spelled and written in impeachable grammar and still be meaningless. In this section, we will look at ways of writing programs that look like they mean one thing but actually means something quite different. We will also discuss contrasts in which things that look reasonable on the surface actually gives undefined results. We will limit ourselves here to things that are not guaranteed to work on any C implementation. We will leave those that might work on some implementation but not others until section 7, which looks like at portability problems. Expression evaluation sequence. Some C operators always evaluate their operands in a known specified order. Others don't. Consider, for instance, the following expression: A less than B and N C less than D. The language definition states that A less than B will be evaluated first, and if A is intended less than B and C less than D must then be evaluated to determine the value of the whole expression. On the other hand, if A is greater than or equal to B, then C is less than D is not evaluated at all. To evaluate A less than B on the other hand, the compiler may evaluate either A or B first on some machines. It may even evaluate them in parallel. Only the 4 C operators and then question mark, color, and specify an order of the evaluation, and then an order evaluate the left operand first and the right operand only if necessary. The question mark colon operator takes 3 operands, A question mark, B colon C evaluate first and then evaluates either P or C depending on the value of A. The operator evaluates its left operand and discards its value, then evaluates its right operand. All other C operators evaluate their operands in undefined order. In particular, the assignment operators do not make any guarantees about evaluation order. For this reason, the following way of copying the first n elements of x, array x to array y does not work. I is equal to 0 if I less than n, y of I is equal to x of I plus plus. The trouble is that there is no guarantee that the address of y will be evaluated before it is incremented. On some implementation, it will, on others, it won't. This similar version fails for the same reason. I is equal to 0, y, I less than n, I plus plus is equal to x of I. On the other hand, this one will work fine. I is equal to 0, while I less than 1, y of I is equal to x of I plus plus. This, of course, be abbreviated for I is equal to 0, I less than n, I plus plus, y of I is equal to x of I. The and or and not operators see as two classes of logical operators that are occasionally interchangeable. The bitwise operators and or and not. The logical operators and or and exclamation. A programmer who substitute one of these operators for the corresponding operator for the other class may be in for a surprise. The programmer may appear to work correctly after such an interchange, but may actually be working only by coincidence. The and or and not operators treat their operands as a sequence of bit and work each bit separately. For example, 10 and 12 is 8, 1, 0, 0, 0 because and looks at the binary representation of 10, 1, 0, 1, 0 and 12, 1, 1, 0, 0 and produces a result that has a bit turned on for each bit that is on the same position of both operands. Similarly, 10 or 12 is 14. 1, 1, 1, 0 and not 10 is minus 11, 1, 1, 1, 1, 0, 1, 0, 1, at least on a 2's complement machine. The and or and exclamation operators, on the other hand, treat their arguments as if they are either true or false, with the convention that represent 0 represents false and any other values represent true. These operators return 1 for true and 0 for false, and the and or operators do not even evaluate the right hand operands if their results can be determined from the left hand operands. Thus, not 10 is 0 because 10 is non-zero, 10 and 12 is 1 because both 10 and 12 are non-zero, and 10 or 12 is 1 because 10 is non-zero. Moreover, 12 is not even evaluated in the later expression, nor is bracket open close in 10 not or bracket open close. Consider the following program function to look for a particular element in a table. I is equal to 0, while I thus and table says and then tab of I not equal to x, I plus plus semicolon. The idea behind this loop is that if I equal to tab size, when the loop terminates, that the element sort was not found. Otherwise, I contains the elements index. Suppose that the and were inadvertently replaced by and in this example, then the loop would probably still appear to work, but would do so only because of two quickly breaks, lucky breaks. The first is that both comparisons in this example are of a sort of that yields 0 if the condition is false and 1 if the condition is true, as long as x and y are both 1 or 0. X and y and x and y will always have the same value. However, if one of the comparisons were to be replaced by one that uses some non-zero value other than 1 to represent true, then the loop would stop working. The second lucky break is that looking just one element of the end of an array is usually harmless, provided that the program does not change that element. The modified program looks past the end of the array because and like and must always evaluate both of its operands. Thus, in the last iteration of the loop, the value of tab I will be fetched even though I is equal to tab size. If tab size is the number of elements in tab, this will fetch a non-existent element of tab. Subscript starts from 0. In most languages, an array with n elements normally has those elements numbered with subscripts ranging from 1 to n inclusive. Not so in C. C array will with n element does not have an element with a subscript of n, as the elements are numbered from 0 to through n minus 1. Because of this, programmers coming from other languages must be specifically careful when using arrays. Init I 10 for I is equal to 1, I less than or equal to 10, I plus plus, A of I is equal to 0. This example intended to set the elements of A to 0 and enhancement of side effect because the comparison in the statement I less than or equal to 10 instead of I less than 10, the non-existent element number 10 of A was set to 0, thus clobbering the word that followed in memory. The compiler on which this program was run allocates memory for users variables in decreasing memory location, so the word turned out to be I. Setting I to 0 made the loop into an infinite loop. C does not always cache actual parameters. The following simple program fragment fails for two reasons. Double S. S is the square root of 2 print %G \S. The first reason is that the square root expects a double value at its argument and it is not getting 1. The second is that it returns a double result, but it is not declared as such. One way to correct it is double S, square root S square root is equal to 2.0. Print a %G \S semicolon. C has two simple rules that control conversion of function arguments. Integer values shorter than and init are converted to init. Floating point values shorter than double are converted into double. All other values are left unconverted. It is the programmer's responsibility to ensure that the arguments to a function are of the right type. Therefore, a programmer uses a function like square root whose parameter is a double must be careful to pass arguments that are float or double type only. The constant 2 is an integer and is therefore of wrong type. When the value of a function is used in an expression, that value is automatically cast to an appropriate type. However, the compiler must know the actual type returned by the function in order to be able to do these functions used without further declaration or assumed to return an integer. So the declaration for such functions are necessary. However, square root returns a double, so it must be declared as such before it can be used successfully. In practice, C implementation generally provide a file that can be brought in with an include statement that contains declaration for library functions like square root, but the writing declaration is still necessary for programmers who write their own function. In other words, for anyone who writes non-trivial C program, here is a more spectacular example made init I character C for I is equal to I less than pi, I plus plus, scanf %G and C, print %G I, braces close, print \n, braces close. Ostensibly, this program reads pi numbers for its standard input and write 0, 1, 2, 3, 4 on its standard output. In fact, it does not always do that. On one compiler, for example, its output is 0, 0, 0, 0, 0, 1, 2, 3, 4. Why? The key is the declaration of C as a character rather than as an init. When you ask scanf to read an integer, it expects a pointer to an integer. What it gets in this case is a pointer to a character. Scanf has no way to tell it did not get what it expected. It treats its input as an integer pointer and stores an integer there. Since an integer takes more memory than a character, this steps on some of the memory near C. Exactly what is near C is the compiler's business. In this case, it turned out to be the lower part of the I. Therefore, each time a value was read for C, it reset I to 0. When the program finally reached the end of file, scanf stopped trying to put new values into C. So I could be incremented normally at the end of the loop. Pointers are not arrays. C programs often adopt the convention that a character string is stored as an array of characters followed by a null character. Suppose we have two such strings S and T, and we want to concatenate them into a single string. Or to do this, we have the usual library function string copy and string cat. The following obvious method does not work. Character stars or string copy or comma S, string concatenation or comma T. The reason is it does not work is that R is not initialized to point anywhere, although R is potentially capable of identifying an area of memory that area does not exist until you allocate it. Let us try again allocating some memory for R. Character R 100, string copy R comma S, concatenate R comma T. This now works as long as the string points to by I's and T are not too big. Unfortunately, C requires us to state the size of an array as a constant. So there is no way to ascertain that R will be big enough. However, most C implementations have a library function called malloc that takes a number of and allocates enough memory for that many characters. There is also usually a function called strlen that tells how many characters are in a string. It may seem, therefore, we would write character star R star malloc bracket open close. R is for malloc strlen upcast plus strlen to string copy R comma s string copy cat concatenate R comma t. This example our fails for two reasons. First, malloc might run out of memory, and even that it generally signals by quietly returning a null pointer. This now works as long as these strings pointed by as and t are not too big. Unfortunately, C requests us to state the size of an array as a constant, so there is no way to be certain that R will be big enough. However, most C implementations have a library function called malloc that takes number and allocation of memory for that many characters. There is also usually a function called strlen that tells how many characters are in a string. It might then seem, therefore, that we could write character R star R star malloc R is malloc strlen s plus strlen t str copy or similar. This example of word fails for two reasons. First, malloc run out of memory, and even it is generally signals by quietly returning a null pointer. Second, and much more important, is that the call malloc does not allocate quite enough memory. Recall the convention that a string is terminated by a null character. The string len function returns the number of characters in the argument string, excluding the null character at the end. Therefore, if strlen s is n, s really requires n plus 1 character to contain it, we must therefore allocate one extra character for R. After doing this and checking that malloc worked, we get character star R star malloc or malloc strlen s strlen 2 plus 1. If not R, complaint exit 1 str copy R comma s str concatenate R comma t. S2 cynic doge cynic doge sin ek duki sin duki is a literary device somewhat like a simile or a metaphor, in which, according to the Oxford English Dictionary, a more comprehensive term is used for a less comprehensive, or vice versa, as the whole for part or part of for whole genus, for species or species for genus, etc. This exactly describes the common C pitfall of confusing a pointer with data to which it points. This is most common for character strings. For example, char star p star q, p is equal to within double quotes x, y, z. It is important to understand that while it is sometimes useful to think of value of p as this string x, y, z after the assignment, this is not really true. Instead, the value of p is pointed to the zeroth element of an array of 4 characters whose values are x, y, z and \0. Thus, we now execute q is equal to p, p is equal to p and q are now 2 pointers to the same part of memory. The character in that memory did not get copied by the assignment. The situation now look like this. The thing to remember is that copying a pointer does not copy the thing it points to. Thus, if after this we were to execute q of 1 is equal to y, q would point to a memory containing the string x, capital Y, z. So would p, because p and q point to the same memory. The null pointer is not the null string. The result of converting an integer to a pointer is implementation dependent, with one important exception. That exception is the constant 0, which is guaranteed to be converted to a pointer that is unequal to any valid pointer. For documentation, this value is often given symbolically defined as null 0. But the effect is the same. The important thing to remember about 0 when used as a pointer is that it must never be dereferenced. In other words, when you have assigned 0 to a pointer value, you must not ask what is in the memory it points to. It is valid to write if p equal to character star 0, but it is not valid to write. If strcmp p character star 0 equal to 0, because strmp always look at the memory address by its argument. If p is a null pointer, it is not even valid to say print of p or print of percentage s comma p. Integer overflow. The C language definition is very specific about what happens when an integer operation overflows or underflows. It either operand is unsigned, the result is unsigned and is defined to be modulo 2n, where n is the word size. If both operands are signed, the result is undefined. Suppose, for example, that a and b are two integer variables known to be non-negative, and you want to test whether a plus b might overflow. One obvious way to do it looks something like this. If a plus b less than 0, complying. In general, this does not work. The point is that once a plus b has overflowed, all bets off as to what the result will be. For example, on some machines, an addition operation such an internal register to one of the port states, positive, negative, 0 or overflow. On such a machine, the compiler would have every right to implement the example given above by adding a and b and checking whether this internal register was in negative state afterwards. If the operation overflowed, the register would be in overflow state and the test will fail. One correct way of doing this particular test relies on the fact that unsigned arithmetic is well defined for all values, as are the conversions between signed and unsigned values. If init unsigned a plus unsigned b less than 0, complying. Shift operator. Two questions seem to cause trouble for people who use shift operators. In a right shift or vacated bits filled with zeros or copies of the signed bit, what values are permitted for the shift count? The answer to the first question is simple, but sometimes implementation dependent. If the item being shifted is unsigned, zeros are shifted in. If the item is signed, implementation is permitted to fill vacated bit questions either with zeros or with copies of the signed bit. If you care about vacated bits in a right shift, declare the variable in question as unsigned. You are then entitled to assume that vacated bits will be set to 0. The answer to the second question is also simple. If the item being shifted is n bits long, then the shift count must be greater than or equal to 0 and strictly less than n. Thus, it is not possible to shift all the bits out of a value in a single operation. For example, if an init is 32 bits and n is an init, it is legal to write n less shifted left shifted 31 times and n left shifted 0, but n left shifted 32 or n left shifted -1. Note that a right shift of a signed integer is generally not equivalent to division by a power of 2 minus even if the implementation copies the sign into the vacated base. To prove this, consider the value of -1 as right shift 1 cannot possibly 0. Thank you.